And no, this one. This is the laser. Okay, let's see if it works first. Let's see if it works. So let's resume the session. Good morning. There will be now a talk by Kazuhiro Shige, which is one of the organizers of the conference. So I'm really happy to have been able to gather all of you here. And it's a pleasure for me to present him. And he will talk about the characterization of F concavity preserved by the Dirichlet heat flow. Please.
Thank you. First, I'd like to say some comments about Professor Marek Fila. I have a very good experience and memory with him, and I have 11 joint works. And the topics are related to the elliptic and parabolic problem with the dynamical boundary condition. And our joint work is kind of the team project. Member is also, of course, Marek Fila, me, and Tatsuki Kawakami. And the role of Marek is like boss of our team, and he always gave us correct direction to the correct direction of our research. And my role is like manager. And actual calculation was done by Tatsuki. And Tatsuki also have a talk about our latest joint work in his talk, I guess. So I'd like to say anything more here. And in the last academic year, Marek visited our university twice. And of course, we discussed about the next project about the heat equation with dynamical boundary condition. Also, at that time, he gave us to the next project related to the semi-linear heat equation with Stefan boundary condition. It is a continuation of his joint work with Professor Suple. And at that time, Marek, after some discussion, Marek contacted with Professor John King, and Professor King gave us a nice conjecture. And we started the project, but the project has been just started. So we have no result now, but probably Professor King give some comments about the project, but I hope you will enjoy, you will join us and try to solve it together. So now that I will start my mathematical part of my talk. This talk is independent of Marek Fila. And this is a joint work with Professor Paolo Sarani from University of Florence and Professor Takatsu is here from Tokyo Metropolitan University. And in this talk, I'd like to talk about the preservation of concavity properties by the direct heat flow in convex domain of array. And basically, this talk is only for linear problem, but possibly at the end of my talk, I use some comment about the semi-linear heat equation. Anyway, I will discuss the linear heat equation. And first, I'd like to introduce the notion of power concavity. which is the most common and useful generalization of the usual concavity property. Okay. Throughout this talk, let omega be a convex domain possible unbounded in Rn. And alpha is a real number or plus minus infinity. And let u be a non-negative function in omega. And we denote by P of u the positive set of u. And we say u is alpha concave, a generalization of the usual concavity in omega if u satisfy the following properties. In the case of alpha equal to infinity, alpha concavity means that the positive set of u is convex and u is just a constant function in positive set. In the case of alpha is positive, this means that u to the power alpha is concave in the positive set of u. And in the case of alpha equal to 0, log of u is concave. And in the case of alpha is negative, u to the power alpha is convex. Okay, in the case of positive alpha, this is concave, but negative case, convex. Finally, in the case of alpha equal to minus infinity, this means that all of a super level set of function u is convex. And we often call zero concavity log concavity, and minus infinity concavity K-psi concavity. Okay, now I'd like to give the two typical examples of power concave function. First one is exponential minus x squared. Of course, this is a variation of the Gauss kernel. So this is an important example in the study of parabolic equation. This function is, of course, not concave, but this is log concave. Because we take log here, then this function minus x squared. Of course, this is concave function. So this is log concave. Second example is 1 over 1 plus x squared. This function is not concave, not log concave, but this is minus half concave. Because we take alpha equal to minus 2, then this is just a root of 1 plus x squared. This function is convex. So from this definition, this function is minus half concave. So by using this notion, we can treat a lot of functions which are not concave in the usual sense. Anyway, among power concavities, we have the following nice property. Let u be alpha concave, let u be alpha concave, and beta is less than alpha. Then u is always beta concave. This means that from this property, we have a hierarchy of the strength of the power concavity among concavity. Indeed, in this direction, the notion of alpha concavity becomes stronger and stronger, and in this direction, weaker and weaker. This means that the minus infinity is the weakest one. So K-psi concavity is the weakest concavity among power concavity. This means that all of power concave functions are K-psi concave. That is, all of super level sets are convex. Okay. Among power concavity, all of the functions are super level sets are convex. And by using the notion of power concavity, there are many results of solutions to elliptic and parabolic equation and from the view of the concavity property. I'd like to introduce some of them. The first result I'd like to introduce here is by Plaskar-Prip in 1976. They proved that initial data phi is log concave in Rn, that log of phi is concave. Okay. In this case, exponential T Laplacian phi, this is the corresponding solution to the heat equation with initial data phi. This function is log concave in Rn for all positive T. This means that heat flow preserves log concavity of initial data forever. And this theory is very beautiful, and proof is based on the so-called Borel-Plaskar-Prip inequality. and kind of linear theory. So the very useful theory, but unfortunately, it is not easy to apply their theories to nonlinear problems. Subsequently, Koreban in 1983 introduced a new method which called concavity maximum principle. And he proved the following. Let omega be a convex domain in Rn, and let U be a solution of the heat equation under the Dirichlet boundary condition. And the initial data of U equal to phi of x in omega. And in this case, okay, similarly to this, initial data, we assume that initial data is log concave in omega. Then corresponding solution U is log concave in omega for all positive t. This result also means that Dirichlet heat flow preserves the log concavity of initial data forever. And also Korebar proved the following. Korebar also discussed the log concavity of the first Dirichlet eigenfunction. That is, okay, let omega be a convex, bounded convex domain Rn, then the first Dirichlet eigenfunction for minus Laplacian omega is log concave in omega. And this theory, his theory is based on the comparison principle. So if the equation has nice structure, then we can apply his argument to the various nonlinear problems. Indeed, Kennington and Cabot extended the idea of Korebar to various nonlinear elliptic problems. For example, okay, this is linear, but okay, they discussed the inhomogeneous elliptic equations, torsion problem, also the nonlinear elliptic problems. And furthermore, after that, Greco and Cabot extended the idea of Kennington at Korebar to various nonlinear parabolic equations, and they proved the preservation of concavities for various nonlinear parabolic equations. And after that, Alvarez-Radrillons introduced a new method based on viscosity solutions, and they discussed of the convexity and the concavity of solution to elliptic problems. And furthermore, Lee and Vasquez studied the preservation of some positive power concavity of the solution to the porous medium equations. And I started some joint work with Paolo Sarani from 2008. And I'd like to explain the first my motivation of this talk, this research. Okay, let's go back to the result by Braskamp-Lieb and Korebar. Okay, as I said before, okay, let omega be a convex domain, and U is a solution of the heat equation under Dirichlet boundary condition. And the initial data is long concave, then corresponding solution is long concave for all positive t. That is, they showed that the preservation of long concavity by the Dirichlet heat flow. And my first question is the following. Is K-side concavity preserved by the Dirichlet heat flow? This result say, okay, if initial data is long concave, then a solution, corresponding solution long concave, that is K-side concave. Okay? Long concavity implies the K-side concavity that all of super levels are convex. So instead of this, if we assume that all of super level set of initial data are convex, then solution preserve such a concavity property. This is my first question. And I have a joint work with this problem with Professor Paolo Sarani. But one-dimensional case answer is yes. This is not difficult because we just apply the theory of number of zeros of solution to one-dimensional heat equation. Then immediately we can get this one. So next step, I would like to try to the higher dimensional case. But after some discussion, we get answer. If n is greater than or equal to 2, answer is no. Okay, this is the example of initial data. Initial data, okay, let initial data be a characteristic function of half space xn is negative, plus characteristic function of some ball is included in this half space. Then asymmetry of initial data, particular in this function, pushed the boundary of the super level set into this direction. Then super level set in some sense like this. This set is not convex, so this is an example of initial data for which KSI concavity is not preserved. For general convex domain, we construct initial data by approximating this function, then we can have some example. This means that for any convex domain, there is some initial data for which corresponding solution is not KSI concave for some positivity. We can prove. Okay, I'll skip this one. So the answer is n equals greater than 2, its answer is no. And after that, we extended this result, and some negative power concavity also is not preserved by directly heat flow. And anyway, 2020, in the joint work with Sarani and Professor Takatsu, we found some concavity property preserved by directly heat flow, but this concavity is not long concave and not power concave. So we found another concavity property, and which is preserved by the directly heat flow. Okay, later I will explain this concavity explicitly, but here we call this property power long concavity. Okay, before this result, for the directly heat flow, only long concavity has been discussed. No other example. But fortunately or unfortunately, I don't know, we found another example of the concavity. So we have the following problems. Okay, first problem is to characterize concavity properties preserved by directly heat flow. First question. Second question, okay, we have some variety of concavity properties preserved by directly heat flow. So second question is to identify the strongest or the weakest concavity property preserved by the directly heat flow. This is the second question. And the third question is, when is KSI concavity preserved? By the result of Braskamp leap and Koreban, if initial data is long concave, then KSI concavity of solution is preserved. But if initial data is not long concave, then what happens? This is the third question. And I struggled this problem for a long time with our Sarani, and from 2020 with Asuka Takatsu. And but today we can show our final answers to these questions. In order to explain our answer, we'd like to introduce a notion of F concavity, which is largest available generalization of power concavity. Okay, I'll introduce the F concavity. But F concavity just means that F, okay, for example, some function F is F concave. This means that capital F of F is concave. So first, I'd like to define the domain of capital F. Let I be the interval 0A, but A is positive and possibly infinity. And let capital F be a function that on the interval I, and the value of F is real number or minus infinity. Okay. Let this function, we say this function is admissible if capital F, the continuous function in the interior of this interval, and F0 equal to minus infinity. Also, F is strictly increasing on I. here I will remark that we don't assume the continuity of capital A at R equal to Z. Also, we define the capital A of omega I. This is a bounded function and I valued bounded function in omega. Then we can, for example, psi belongs to A omega I, then we can define capital F of psi. And we can define the concavity. Okay, let F be admissible on I. Okay, that is a continuous interior of I, F0 equal to minus infinity, F is strictly increasing. And okay, for any I-valued bounded function psi in omega, we say that psi is concave in omega if F of psi satisfies this inequality. That is, F of psi is concave. And okay, by using this concavity, I'd like to explain the power concavity again. In the case of power concavity, interval I just 0 infinity. And if we set F of tau equal to 1 over alpha, tau alpha, minus 1 is not so important. Just alpha tends to 0, then this function is converged to log tau by the effect of minus 1. So I add minus 1, but this is not so important. Okay, if this function is, of course, strictly increasing, and alpha is positive, this function is not continuous at tau equals 0. But by capital F is admissible, and power concavity is one example of the concavity. And the next example is power law concavity. This is kind of the combination of usual power concavity and long concavity. In this case, I equal to interval I is 0, 1. And we set L alpha tau is minus log tau to the power alpha. W minus implies that this function is increasing. And this function is admissible, this interval, so we can define the L alpha concavity. And we call this concavity alpha log concavity. Okay, I'd like to give some comments about this concavity. In the case of alpha equal to 1, this concavity corresponds to the usual log concavity, so somewhat standard. And let F be alpha log concave, and alpha is less than beta, then F is beta log concave. This means that among log concavity, there are some hierarchy with respect to the strength of concavity property. Also, okay, we consider the exponential minus x square. This is important for parabolification, of course. This function belongs to is half log concave. Half log concavity is the most suitable concavity exponential minus x square has. Because we take this function, then we put exponent x squared to tau equal to this one, then it is just a linear function. So this is the optimal concavity property for this function. So okay, this is the important for parabolic equation. So we can expect some power log concavity should be preserved by the heat flow. Indeed, we can show that alpha log concavity with alpha is less than 1, that is stronger than log concavity. And alpha is greater than or equal to half. Okay, half case is this one. In this case, this long concavity is preserved by the direct heat flow for any convex domains. So in this sense, half long concavity is very important in the study of the direct heat flow. And third one is more important. Let H be a one-dimensional heat equation with initial data is just a characteristic function of 0 infinity at t equal to 1. Okay, by the good property of the heat equation, this function h is positive and smaller than 1. and increasing with respect to C. So we can define the inverse function of H, that is capital H. And the domain of capital H is interval 0, 1. And capital H is strictly increasing. So finally we set H0 equal to minus infinity, then this capital H admissible, interval 0, 1. So next, I'd like to define the admissible function, the interval 0a. We modify this function as follows. A is bounded, then HA of tau equal to H of tau over A. Also, A equal to infinity, we say this function of tau. Then HA concavity, this function HA is admissible in the interval 0a. So we can define HA concavity. And we call HA concavity hot concavity in our research, in our study. Okay. And in order to solve our problems, we have to define the strength and the weak strength of F concavity, but it's kind of the generalization of the power concavity. Omega be convex domains, and F1 and F2 admissible on some interval I. And we define the C omega Fi is a set of Fi concave function in omega. And we say F1 concavity is weaker than F2 concavity if a set of F2 concave function in omega is a subset of F1 concave function in omega. Okay, this is just a generalization. So not so difficult, I think. Okay, I'll skip. So now I'd like to state our main result of this talk. First result is to relate the strongest F concavity preserved by the Dirichlet heat flow. Let omega be an interval 0a and omega be a convex domain in Rn. Then, because we can define the HA concavity similar to the previous sheet. Then HA concavity is preserved by the Dirichlet heat flow in omega. Second assertion is the following. Assume that a capital F be admissible on I, and then we can define the F concavity. And we assume that F concavity is preserved by Dirichlet heat flow in omega. Then F concavity is weaker than HA concavity. This, okay, HA concavity preserved, and for any F concavity preserved by Dirichlet heat flow, Dirichlet flow is weaker than HA concavity. This means that HA concavity is strongest F concavity preserved by the Dirichlet heat flow. Also, okay, in the definition admissibility of capital F, we don't assume the continuity of F at tau equal to 0. But if F concavity preserves the Dirichlet heat flow, then limit of FR R tend to 0 equal to minus infinity. So we get some. We need some continuity at tau R equal to 0. The second theorem is related to the weakest F concavity preserved by the Dirichlet heat flow. Let F be admissible on I again, and let omega be a convex domain in Rn with N is greater than or equal to 2. Because one-dimensional K-psi concavity preserved, I explained. So the weakest concavity preserved the Dirichlet heat flow is K-psi concavity. So now here we assume that the N is greater than or equal to 2. Okay, assume that F concavity preserved by Dirichlet heat flow in omega. Then F concavity is stronger than long concavity. Okay. Of course, already we know long concavity is preserved. So the long concavity is the weakest F concavity preserved the Dirichlet heat flow. Second question is second result is about if F concavity at the initial data is not long concavity. Okay, assume that F concavity is not stronger than long concavity. Then there exists some initial data with phi initial data is 0. So this is on the boundary, you mistake. And phi is F concave. Okay, phi is F concave, but this F concavity is not stronger than long concavity. Then exponential T Laplace omega is not K-psi concave in omega for some T positive. Okay. This means that, for example, F concavity is not included long concavity, then for some initial data, some initial F concave function, corresponding solution is not K-psi concave. K-psi concave is the weakest concavity also among the concavity. This means that the solution loses every concavity property or sometime. We cannot expect any concavity property for this case. So if we need some concavity property, we should assume initial data is long concave. This result thing. And okay, combine everything. And we consider the most important case A equal to infinity. In this case, HA concavity coincides with concavity. So this, okay, by combine everything, let omega be a convex domain Rn with n is greater than 2, then F concavity is preserved by the Dirichlet heat flow in omega if and only if F concavity coincides with long concavity. Coincide mean this implies that this is if and only F term is some positive constant A times log tau plus B. This is just a long concavity. Okay, when I was a student in master course, I started studying the concavity property. And at that time, I learned by result by Porebar and Greco-Cabor and blah, blah, blah. So I thought why log concavity was only discussed. Of course, I didn't obtain any answer, but by using the result of this corollary, their considerations are good, perfect. Because if initial data is not long concave, generally we cannot expect anything. So the consideration of Cabor and Greco, yeah, was correct. This is the answer. Okay, but okay, we have some problem in the case of n equal to 1. So in the next slide, I'd like to discuss the one-dimensional case. In this case, we assume the some regularity of capital F. Indeed, we assume C2 regularity of capital F. Then we get the following. F admissible on some interval I, and omega is a convex domain in Rn, and the F has a C2 regularity. Then F concavity preserved by Dirichlet heat flow if and only if F satisfies these three conditions. Now, if we assume some regularity of F, we can obtain the sufficient necessary condition of F to be preserved by Dirichlet heat flow. Okay, in the first theorem, F concavity preserved the heat flow, then F satisfies this. Also, under this assumption, F prime, okay, in admissibility of capital F, F is strictly increasing. But we don't assume F prime is positive. But under this condition, F prime must be positive. Also, we need some condition, and this capital F is the inverse function of capital F. Indeed, in the case of long concavity, this function is just constant 1. And in the case of hot concavity, this is a linear function. So in some sense, constant and linear function is the ultimate concave function. So it is natural, I think. Okay, we obtained the following rough conclusion. HA concavity is the strongest F concavity preserved by the Dirichlet heat flow. Second conclusion is concavity is the weakest F concavity preserved by Dirichlet heat flow when n is greater than or equal to 2. And one-dimensional case, non-concavity and K-side concavity, only non-concavity and K-side concavity are preserved. And if F concavity is not stronger than non-concavity, then there exists some F concave function such that corresponding solution to this initial data phi is not K-side concave in omega for some T positive. We cannot expect any concavity property for this initial data. These are our conclusions. Okay, next I'd like to explain some ideas for the proofs. First, I'd like to explain how to obtain disruption of K-side concavity. In our theorem, if initial data is not weaker than long concavity, then we have to prove some initial data the solution for some solution should be not K-side concave. And in my first joint work, Paolo Sarani, we can show the non-convexity of super level set by using the asymmetry of initial data. And after that, we wrote some paper. At that time, we used this example by using the difference of decay of exponential decay and difference of decay of exponential Gauss kernel and initial data. And in this paper, in this result, we can check the directly of the convexity and non-convexity of some super level set. Generally, it is not easy to check the convexity of super level set, of course, but heat equation, as you know, of course, you know very well, the heat equation is very nice. Because in two-dimensional case, if initial data is separate variable, some function of x1 times a function of variable x2. In that case, corresponding solution to the heat equation is just this one-dimensional solution times the other one-dimensional solution. Probably we can expect some related result for fractional diffusion equation, but fractional diffusion case, we don't have this relation. So unfortunately, our argument is not applicable to the other case. But okay, this function is well known. Also, this function is well known. So we can check the non-convexity of initial data, so some super levels. Then we can get something. And on the other hand, I will explain the strategy to prove the preservation of concavity. Okay. Let U is a concave if and only f of U is concave. And first, I try to show this concavity by applying the Corey-Barlow-Kennington argument, but it's not so good. Instead of this concavity, we set V equal to exponential of F. Then F concavity of small u is equivalent to log concavity of V. Then, fortunately, we have already established the preservation of log concavity for general nonlinear parabolic equation, and we applied our previous results. The result is based on the viscous solution, so that we can get the preservation of concavity under some suitable sufficient conditions. On the other hand, we applied some result, applied or developed the argument by Kolesnikov, and then we can check this sufficient condition necessary. We are really lucky. I'll skip. So okay, I'll explain the applications. This is nonlinear. Okay, I discussed about the concavity preserved directly heat flow, but their result is also applicable to this seminar heat equation, absorption case. this case, the same conclusion as directly heat block holds. But if we consider plus the Fujita equation, then any F concavity is not preserved, except for one-dimensional KSI concavity. Before, I imagine that if initial data has nice concavity property, then solution blows up, but have some KSI concavity, and I hope that the graph set is only 1 point. I imagine, but this strategy was not good. It's not good. This is just it. Okay. Of course, our result applicable to the parabola equation with variable coefficient. Okay. Finally, I'd like to say something about future works. Okay, I'd like to discuss eventual concavity. This result proved the real basket. And they show that, okay, this is the heat equation in Rn, and initial data is bounded and have a compact support. Then there is some positivity. Solution U is non-concave in Rn if T is sufficiently large. We call this property eventual concavity. And in the joint work with Sarani and Takatsu, we show that alpha long concavity, okay, solution U is alpha long concave for all sufficiently large T. If alpha is yes, alpha is larger than half, we can show. So okay, Gauss kernel has half a long concavity, as I said. So probably it should expect, we expect that critical case also eventually alpha, half eventually long concavity should be false for in the heat equation. This is the open problem. And recently, I offered some answer to this question. If initial data has nice decay from the boundary of the compact support with initial data, then solution has half, eventually half long concave, we can show. But the argument is very delicate, and we cannot apply this argument to half space, the other case. So I hope that we can obtain we can construct qualitative properties for this direction. But now, the result by Rienne Vasquez and me, we just calculate and just check the concavity property. So it is not so easy to get this property for under the general assumption, but I'd like to do that. And that's all. Thank you for your kind attention.
So are there some questions? Okay. First.
Okay, that's the question. What is known if you replace diffusion operators, Laplacian, by a nonlinear diffusion operator like a Paulus medium in Laplace?
Of course, Professor Vasquez.
There was a paper by Hamilton and
Yes.
Totti and Scalopoulos in PMD, where they proved that porous medium has the pressure is 1/2.
Yes, yes.
So alpha equals 1/2 works for porous medium.
Yes. Yes. Also, we can check the optimality of the half of n minus 1 concavity for porous medium equation. Then probably we can generalize the result in this test. Probably we can get some concavity, but now we don't try. Probably yeah.
And the idea of what we proved then with TMD was that if the attractor is strictly low concave or alpha concave, then eventual concavity will happen for the flow. And this could be true, for instance, for all of the general equations, right? It's not true.
Yeah.
It's an open problem.
Yeah, in our study, we need a 2 stage. At the final stage, okay, we probably eventual concavity help the study. But at the initial time, some cases, some concavity is not preserved. So we discuss both cases.
So alpha equals 1/2 is the best for you.
Probably.
It's still open
Yes. Pressure.
in your case. Alpha equals 1/2. It's still open.
Alpha long concavity is optimal. In the previous talk, okay, I had some talk to you. At that time, we couldn't say anything. But now, among power long concavity, half long concavity is the best, strongest.
So in the case of the Euclidean space, when you study, you get the log concavity starting from an initially compactly supported solution by the Lee-Vasquez result. Do you have a guess of what could be the behavior at infinity, for instance, which guarantees log concavity in finite time? For instance, it would make sense to have higher order moments or maybe exponential moments finite against the initial datum. And there are some results on stability and lots of inequality that point in this direction.
The last time concavity property for solution for large time t, we have to control the behavior of the space infinity. It's the most difficult point. So if we can control something, then of course we can get something, but we don't have any more result now.
There are no other questions. Let's take the speaker again. Now we make like 3-minute break because we have to set up the next talk, which will be in honor of Marek. So.
Riccardo can anche but I have no idea where
What is this? Okay. Oh, what is this? Here. What?
Yes.
Good morning, everyone. This is a special session because of the sudden demise of our good friend Marek Fila, who was a very instrumental person in organizing this series of workshops. We are going to speak three persons who are related to him in representation of all the group of people who have been working with Marek. Marek Fila is known in some sense as the person who started to blow up into Slovakia. There were no mathematics coming from Slovakia that were popular around. There were some mathematicians, of course. But Marek was very instrumental in making a certain promotion of the place. We went to Bratislava to meet him. And he died in April 23, when we were already organizing this meeting. Marek I will give you in my introduction a series of data about his official life. So I'm taking my information from web pages in Bratislava and from Wikipedia. And he was a Slovak mathematician, and his main research focus was diffusion equations and partial differential equations. This is what they say. And he was among the most productive scientists in Slovakia. This is what they say. He was a very friendly person. This is what I say. And he was very oriented to international cooperation, which is a foundation character of our community. We are going to be international or nothing. And he was a great organizer of research in his country and his town and all over the world. As a data of his life, he was born in Bratislava in 1959 to an artistic family. Father was a painter, Rudolf. His mother, Dorota Filova, was a well-known renovator of medieval art. You see that ladies in Czech have an ending, Fila, Filova. Okay. So it's easy to recognize the names, but they are not the same name in masculine and feminine. Well, he studied mathematics in Comenius University, graduating in '89, and his doctoral advisor was a person that is very well known in some sense, Pavel Brunowski, and he was Brunowski also the advisor of another very good Slovak mathematician who is working now in the United States, Peter Polacek. He's also our friend. Following his graduation, he remained at the university and became a full professor in 2008. Okay. This is more or less his life. What is important for us is the second slide. It says that in 90s, he was, it appeared in my life because he was visiting USA, in particular Iowa State University in Ames, Iowa. So it is a very rural place where you can be interested in cows and mathematics. And he was interested in mathematics. In fact, he worked with the prestigious Professor Howard Levine. He was one of the persons who was promoting the study of nonlinear diffusion equations related to blow-up. So this is very important for opening up his ideas of what is research. And then I met him there in the spring of 91. I was visiting Minnesota, and Howard called me, listen, come in, you can talk to me and to this young Slovak fella. And we became friends ever since. And then later he was a visitor to the University of Tokyo. And AG there will report on his deep connection with Japan. He was the person who brought Japan to our lives. He founded the Department of Applied Mathematics and Statistics at the Faculty of Mathematics and Physics of Comenius University, and he led it for 11 years. Mathematics, the applied science in international level was not much in Bratislava, so he did a lot to make it work. Let's go to practical things. In 2004, he had this wonderful idea of putting his knowledge of Japan in the form of European-Japanese workshop on blow-up, and I was honored with the invitation to give a lecture there on the topic that I didn't follow very much, introducing blow-up, no, blow down into the world of blow-up. In fact, the idea is that things that are regular in blow-up problems end up being singular. And what I discovered in logarithmic diffusion is that initial data that are singular end up being regular, which is, well, okay, so I gave a lecture about something new. And everything went well, and they invited the group in Spain to organize the second workshop in El Escorial, Madrid. And we were very interested in bringing interesting people, and the interesting person then was Hiroshi Fujita, eminent professor in blow-up. I mean, Fujita equation and Fujita exponents are like important concepts in our community. Professor Fujita was very happy in Spain. We had a big problem with finding his suitcase, but everything went well at the end. And then there were workshops. For instance, I quote here the fourth because I was there in Leiden, Holland, with our friend Holshoff, who was instrumental in organizing these things. There were other people in Europe involved in that, like Tertikas, Winkler, Supple. So there were many people. And the workshops, Euro-Japanese, went on until 2016. And then, okay, more or less they disappeared, and Marek was a bit ill, and he had a long illness. He had accepted to be part of our scientific committee of this workshop, but Phil's death was announced to the department at April 23. So we were surprised and very sad, but that's life. All of us will go in due time. And then I took from the page on his page in Bratislava a tribute to his memory by his colleague Richard Collard. And I took the time to Google myself to translate into Spanish the thing that was written, Zamarek film in Slovak. It says interesting things, his friend Collard, that Marek was interested in blow-up, so-called blow-up, because blow-up is nice. We know blow-up, but most of people don't know blow-up. So blow-up is very interesting new word. And he explains that some solutions or their derivatives In the case of sublet, is the derivatives. In the case of the rest pass, it's the solutions. May in the final time reach infinite values. And this may seem to the casual reader an abstraction that doesn't have any use. And in fact, it is not true, because in the applications, there are concentrations that follow approximately our equations, and they try to gather around and lump together. And this lumping together is what the singularity tries to describe. And when they are very close together, the equations of all these disappear, and you get something called the coagulation regime. Okay, so Marek wondered under what conditions the phenomena occur. So it's a problem that in principle was very applied. Try to understand what happens when they begin to get together. What are the shapes? In which shape? Are they radially symmetric? Will they go around the point? The singularity is isolated. How quickly they go? And for instance, also, can you continue the evolution in some time? Some more time in some sense, because life does not stop or blow up. These bacteria, these cells will continue to do something. So is there any continuation? And this problem of continuation is very important because in biology and chemistry, life continues. And well, we have to give it some sense. Maybe as let's say yesterday, you can get weak sense, viscosity sense. Maybe some of the boundary conditions are not true, but is there something that we can call a physical condition, a physical solution? So this is the big problem for us, getting physical solutions that are not classical solutions. And I finish, Marek's results brought understanding into problems that are not easy to explain. The methods used for their solution are not at all easy to understand. This is his colleague that says that it's difficult to understand. But in the mathematical language, however, and for us, we are experts in these things, these concepts are very well understandable in formula. We are very happy that we are able to explain them. Problem is explained to the rest of the community of mathematicians. His colleague says that his articles and each of his lectures was interesting story. The story of solutions of differential equations that go into the future shape full of attractive patterns. So you have to get the pattern to where they go. Some of these patterns are Gaussian, some of them are not. We are very interested in the ones that are not Gaussian, and why? Why they are not very Gaussian? This is very important. So Kohler finishes by saying it was some days before Marek passed away. Even if he was not expected to attend the meeting, Marek was at all lectures and that they had on Wednesday. He told me that it was great that we still have so many excellent students who do very well non-trivial things. And the emphasis now is in non-trivial. Don't do trivial things for the public, do it for yourself if you like. And this Marek is no more with us, just Jehovah Pamięć, honor to his. End of this part. Next.
So Marek was one of my best mathematical friends. He fed me a number of interesting problems down the years. I view him as, I'm biased, but I view him as having an exceptional understanding of the roles formal methods can play in building up towards rigorous proofs. So I'm going to do two things, talk about the last problem he gave me very briefly, and then a few reflections. So this is the email it started with. The previous problem I will also very briefly mention, which we talked about in Equidif Leiden, which was the last time I saw him, which was immediately before COVID. So I guess we were in physical contact for about 20 years. Yeah, so it's nice to have this memory of when we did meet. I'm about to tell you what the problem was. Marek was very keen on it. Right, these slides are very scruffy, and the reason for that is I decided the most appropriate thing to do was to show you what I sent to Marek. It shows you what he put up with and what he converted, the kind of thing he converted into something meaningful. So there were 4 sides of A4, it turns into 8 slides. It's only the first 2 slides that I seriously want to talk about. So the problem is the one recorded at the top. So Stefan conditions at a free boundary, top right, but beyond the usual Stefan problem because of the blow-up style source term. So view it as a phase change with a chemical reaction going on. There are 2 known cases, asymptotic behaviors that Marek and collaborators had analysed. One was corresponded to blow-up, which is in effect where you can think of the diffusion term being absent. The other was where it extinguishes, and then you can think of the source term being absent. So there was that dichotomy of outcomes. As soon as you have that kind of dichotomy in this context, there's at least a trichotomy because there has to be something that sits between the 2. So that was the question Marek asked me, and here's my rough and ready analysis of it. So I've mentioned the 2 balances that give you the dichotomy. You ignore the source term or you ignore the diffusion term. This problem is very nice that the borderline, you ignore the only other term, you ignore the time derivative. So you simply write down a quasi-steady balance as recorded there. You go through the scaling arguments that concur with the free boundary conditions, and you determine that the conjecture for the behavior in this borderline case is as recorded there. So I did want to do these technical details, both to maybe give you some indications of the way Marek worked, but also because I wanted to encourage people to work on it because it would have pleased Marek. And I've been delighted to hear at this meeting there is activity on this. I'm only around today, this meeting, so if there's more details to tell me, please do. And you can fully specify everything, the constant that determines the profile and the location of the free boundary. All the other stuff was about stability, which I did a very crude analysis of. You want the borderline case to have a single unstable direction to be a true borderline. So I plowed through that. I'm not going to subject you to it. The only comment is a real comment is the one at the bottom that the stability problem in some sense corresponds to a much better known problem with a fixed domain where you want a borderline between blow up and extinction. And in that case, the borderline is the steady state. In this case, it's the quasi-steady state. And I think there's something slightly interesting mathematically there, because when you have a quasi-steady state rather than a steady state, there's a meaningful time translation mode you don't have when the thing is a true steady state. So that was the conclusion of the notes I sent to Marek. And this was his response. So typical Marek, very encouraging. And this brings us back to where we are now. I'm at this meeting because of Marek in two different senses. So thank you, Marek. One of the reasons I could tell Marek's problems were good ones was that they were never dead ends. They always raised additional questions. So in the case I've just talked about, it turns out that the linear PDE, the behavior is more complicated, somewhat surprisingly. So if people are interested in pursuing that, let me know. That was my final email exchange with Marek, and he clearly was interested. The previous problem, the one I talked to him about at Leiden, relates to the things Ishi said yesterday. The only thing I want to say now is I was slightly disconcerted to find I could construct what I assume is a new solution to the fast diffusion equation with an arbitrary constant in for a very special dimension, which is the one AG mentioned yesterday. So I haven't seen that exceptional exponent in any other context except for n equals 2 when it's BG flow. AG understands this stuff much better than me, and I hope he finds time to explain it to me at some point. Okay, I think that was all my slides. Just check, yeah. He was one of my best mathematical friends, so some reflections on that. You don't have to be similar people. I think we were quite dissimilar. He travelled a lot and he was very good at it. I seem to be extremely bad at travelling. he was significantly more sociable than I naturally am. I talked to Joost Hulshoff about this a couple of weeks ago, and his comments about Marek were rather similar to the ones I'm going to make. I guess Joost was more like him in character than I am. So mathematical friends, you have to be interested in the same kind of problems. So the ones we're interested in can be viewed as slightly esoteric, these kind of borderline cases. But I think they often are important, and they're certainly often very difficult. While we're dissimilar in personality, we're also quite dissimilar in mathematical methodologies. He was rigorous and perceptive, very perceptive in those grounds. I'm English, so I'm essentially entirely formal. But I think that kind of combination often works better than when you are similar. You're doing different things in the same context rather than duplicating. The collaboration has to be enjoyable, and with Marek it always was. He said what he thought, which was useful because it saves a lot of time when you can be honest with each other when you're getting things wrong. But we had laughs, it was fun. And finally, he was a very loyal collaborator. He encouraged two very good Slovak students to do PhDs at Nottingham. And I'm pleased to say they're doing very well still. So those are my remarks. Marek Fiedler was one of my best mathematical friends. I will regularly miss him because I repeatedly come up with problems where the first thing I think about is what would Marek say about this. And so thank you, Marek, and I will finish there.
Well, please note about how Marek should be a very attentive person to what you were doing. So that listening is important. You could translate the discussions with you into open problems. So I agree with John. Please.
Okay, let me start. So yesterday, I was a bit emotional, so I forgot to express my gratitude. So let me take this opportunity to thank the organizers for giving me a chance to come to Madrid, and especially the local organizers for their support, hospitality, and the support from the ICMAT. So, as one mentioned, Mike Fiedler has a deep connection with the Mathematical Society of Japan. So in this short talk, let me explain his activity related to Japan. Because his first visit to Japan was probably 1998 or 1999, invited by Matano to the University of Tokyo. So since then, he visited Japan kind of regularly, probably at least a few times every year. So it's impossible to count how many times he visited Japan. Also, in many cases, he gave a seminar talk, or maybe he gave invited lectures. So it's impossible to list all talks. So here, let me only introduce you his official visit to Japan, and also about his intensive lectures delivered in several universities. Okay, so the first official visit to Japan is by the bilateral program for joint research projects. This is basically for 2 years program, supported by JSPS, Japan Society for the Promotion of Science. So with Marek Fiedler, Peter Polaczyk, and Matano, we applied for a grant from name title like this, and it's basically two program between two countries. So this is for Slovakia and Japan. So fortunately, the application was accepted. So we had many chances to visit each other. And actually, when during this program, I started the collaboration with Marek. And it turned out to be very, very successful. So this is very lucky that this program was accepted. The second official visit of Marek is supported by the 21st Century COE program. So COE means Center of Excellence at the University of Tokyo in 2004. And so the title of this program is like this. So this is the base for the new development of mathematics to science and technology. So he stayed in Tokyo for 6 months. And during his stay, he gave a series of lectures, 8 times, okay, 8 time intensive lectures. And so they titled Introduction to the Blow-up Problem for Nonlinear Parabolic Equations. So this lecture was, the lecture note for this course was edited by Shimojo and Matano, and it's published as one of the series of lecture notes in mathematical sciences in University of Tokyo. So fortunately or unfortunately, it was in Japanese. It's good for Japanese people, but may not be good to other people in other countries. But this is the title page of the lecture note. Here, okay, let me translate these Chinese characters. Okay, so this means that the nonlinear heat equations and blow-up problems introduction. So this is the lecture note. Okay, so here is the name of Shimojo. Shimojo is there. He took this course when he was. Are you a student? Were you a student at that time? Yes. So he edited this his lecture note and they were published later. And okay, this is the contents of his lectures, this lecture note. So this is about the existence of stationary solutions, definition blow-up in bounded domains, blow-up solutions, boundedness of type Riemann solutions, universal estimate of global and blow-up solutions, continuations after blow-up and complete blow-up, incomplete blow-up, realization after incomplete blow-up. So this is the whole about the whole story on this blow-up problem. So this is really a useful lecture note for, at least for Japanese mathematicians. And okay, the third official visit was supported by 21st Century COE program. Again, it's misspelled here. And at the Tohoku University in 2007. So this program, actually I was involved with this program as well. And this is actually program the physics department and mathematics department. So this is the title, Exploring New Science by Bridging Particle Matter Hierarchy. So it doesn't look like mathematics, but anyway, we invited Marek Fila for maybe a few months or so, or maybe as a guest professor for 1 semester. So during his stay, he gave intensive lectures for science. So the title is Blow-up of Solutions of Semi-Linear Parabolic Equations. And so this is the program of the, okay, this content of his intensive lectures. Okay, so there's so many, it's not easy to translate. It's so complicated, but it was done in this week. So it's May from 8th to 12th. He gave 4 lectures, and the title of is this here. Yeah, this is the content is the sufficient condition for blow-up and blow-up set, rate of blow-up profile, complete blow-up, beyond blow-up, immediate regularization blow-up, boundedness of blow-up solutions. So at that time, these are actually the state-of-art topics in this field that he gave us the very new directions in this field, the research in this field. This is the fourth official visit to Japan, supported by the Research Abroad and the Invitation Program for International Collaboration. This was supported by the Interactive Research Center of Science in Tokyo Institute of Technology. In this year, I was working there in Tokyo Tech. So I applied for this program, then fortunately it was accepted. So he was invited as again, I guess, the professor of the Tokyo Institute of Technology, and he gave a series of lectures in June. Yeah. So this is the title of his lectures, but unfortunately I lost the details, so I couldn't find the details in my laptop. So I'm sorry, no on here. And okay. So the fifth visit was official visit was a workshop on linear power PDGs and related fields in honor of the 60th birthday of Marek Fila and Peter Polacek. So this was organized by Kazuhiro Ishige there, Tatsuki Kawakami, and also Tsuhito Miyamoto, and supported by JSPS and FMSP. I don't know what FMSP means, but yeah, supported by this. And so this was yes, a very interesting. Yes. So that's some. Okay, this is actually the part of the program. Okay, so this is the title of this workshop. And that's the first speaker.
Mr. Michael Winkler.
Yeah, Michael Winkler, the first speaker.
Very good student with
Yes.
Fila.
So he actually, Michael Winkler published more than 20 papers with Marek. Yeah, he's the most co-author.
Oh yeah, he was very strong.
I'm the second, actually.
Very strong advice.
Yes. And also there are many others, but okay, here is a talk by Marek Fila, continuation beyond interior gradient developing linear power equation.
This is what Professor Korar was talking about. The evolution after roll-up has to be true.
Okay, Peter, name here, Peter Polacek is also a colleague of Marek Fila, so they both of them were invited. So this here is the names of organizers. Oh, FMSP, this leading graduate course for
Listen, let me interrupt you. Peter Polacek is a very important person because he has some strange things. He says multiplicity of cell-similar solutions of the cell-similar heat equation. Why multiplicity? Why multiplicity? So it always is an open problem.
Actually, is this really his work? I don't remember what he talked about.
He's a very interesting person.
Yeah, he's a really very good mathematician. He's one of my best collaborators. Okay, so this is the last part of the program. This is a 2-day workshop, but this is really good. Okay. So he had a very strong. He influenced a lot to the community mathematics in Japan, and actually he was so nice to young researchers, and he was so good to students. So many young mathematicians were stimulated by his lectures, anyway, he visited so quite often to Japan, and so he had many collaborators in Japan, many Japanese collaborators. So then he published 37 joint papers with Japanese mathematicians. Here is the list. I have published 16 papers with Marek, Ishige, and Kawakami 10 papers. It may be the new one, so he said 11. Okay, so maybe the new one probably. and 6 papers with Matano, 4 papers with Takojin Takahashi, and 2 papers with Ninomiya, and 1 paper with Noriko Mizuguchi. Actually, there is another Japanese collaborator. He used to be must be a student of the Iowa. A student of probably Howard Levine, but anyway, when he was visiting Iowa, so he worked with, maybe he took care of the Japanese students. So,
I remember that this paper with Hirokazu Ninomiya was one of them was written in Bratislava during a conference with me. We began working frantically in the middle of the workshop, and at the end there was a paper.
Diffusion in this global, diffusion in this global existence, something like that.
Yeah. They were very, very good at working during conferences.
Yes, so successful. That's great. Okay. So these are his academic activities in Japan, and his last visit to Japan was in February of this year. And so then we have a chance to. Okay, so these are academic activities, and the rest is about his personal activities in Japan. So this, as you may know, that Marek liked beer so much. He always insists that the best beer in the world is the Czech beer. Maybe Pilsner Urquell or something. Probably Pilsner Urquell, what he invented. But I believe he loved Japanese beer as well. And he said that maybe he said that Japanese is good enough. Okay, but probably it means that it's good, so good, because his standard for beer is very high. Okay. So I believe that Japanese beer is second best for Marek, I believe. And also he loved izakaya so much. Izakaya is a Japanese style pub. And he serves beer and many various kind of alcohols with some foods. And his favorite is nomihoda, which means all you can drink with a fixed price. Okay. So when sometimes we went together to the izakaya, and when we requested the nomihoda, he understood some Japanese, and he was so happy with this. And he likes Japanese food as well. And his favorite is this one. This is sabamiso. It's a fish, okay? Seafood. So this is the mackerel cooked with miso soup, miso sauce. He loves this so much. So it's really a good combination with white rice. Okay. So if you have a chance to go to Japan, please try this. So Marek said that the best one is available in the Tohoku University. Just go to the Mensa, then you can find this. So he really loved this one. And so Marek has a very deep knowledge about the Japanese culture as well. So Professor Vasquez said his parents are artists. Actually, he inherited the ukiyo-e paintings from his father, and these are famous ukiyo-e paintings. And maybe you know he has a very nice collections of ukiyo-e, original ones. So when I went to his apartment, he sometimes showed me a bunch of ukiyo-e paintings. Must be very expensive, but he just put it in the storage. And that didn't seem to care so much, but anyway, it must be very good collections. Okay, so this is the last slide, and okay, this I wanted to show you more photos, but unfortunately, I don't keep good photos. This seems to be the best one, which this photo was taken several years ago. I tried to find a good photo in Japan, but this was this is the pedestrian path near the community university. This is a tram railroad. So anyway, she's in what she's in this smile. Okay, so this is the last slide. Okay, thank you so much for coming out there.
Well, this is part of what the community was able to see in Marek, his love of open problems, his idea of pushing the calculations to see where you go, not trying to write a paper that you already know the solution. As Jonkin said, he wanted to know where the problem was trying to lead you, right, and go in that direction. And then there are a number of people who were attached to talk to him. We said something about the ones that are not here, like Winkler, Holzhoff, Tertikas, who plays here. And I think that it is very nice that our community honors his memory. So I propose that we finish the session with 1 minute of silence in honor of Professor Marek. Thank you. Let's proceed with life. Gambate. Hey G, let's take a picture.
Parli adesso? Parli adesso? Dagliela Carlo, Gabriele, dagliela Carlo.
This is a good background to take a picture. It's very much him when he was happy.
Sì. Mira, quello es, ella es la fotógrafa oficial, entre comillas.
Okay. Primero nosotros tres y después los ordenamos también. Que venga ahora también.
You three.
No nos vamos.
Eh? I think you should move a bit more because you have the thing in the face. Luis, poco más. Luis, poco más. Poco más. Yes, también.
Ahora, y con los organizadores que Goro.
Goro.
Una foto con los organizadores. It's an official celebration.
Okay, then she will send it me low and high quality. With the quality of the no, because if you send it by WhatsApp, it's low quality. So
Yeah.
send it to me, Dropbox.
Okay.